All right, let's get started. So today we're going to talk about quite a different kind of a security concern that we haven't covered yet, and it's side channels. It's a fairly, quite a different kind of a security worry that we haven't quite looked at in detail yet in this class. So in general, side channels like the one you read about in this paper are sort of any kind of ways in which a security system reveals information in a way that wasn't expected by the designer. So it's a little bit abstract. So let me try to describe what I mean. So we have some kind of a system that we care about protecting. Often it has some secrets that it needs to keep. It might be actual secret data, or often could be just a cryptographic key that is really important that this key doesn't get revealed. And the system processes some kinds of requests, takes messages in, sends responses out, replies. And if we just look at the requests and responses, maybe things are actually looking pretty well, and we don't have a security problem. But what security researchers have figured out is that often computer systems leak information in all kinds of ways. So one of these ways that this paper sort of talks about is timing information might be revealed from a computer system. So maybe the timing reveals some information that you didn't want to leak as the designer of that system. A more sort of classical kind of a side channel might be that there's RF signals emanating from your computer while it's running. Another example might be that your computer is running and is having different power utilization, or the amount of power it's using sort of depends on exactly the key that is inside of it. Maybe you can guess the key by looking at how much power your computer is using. And maybe there's audio effects as well. It's like when my computer, for example, is under heavy load, it makes a whistling sort of a sound from some oscillations. And if it's really heavy load, the fan kicks on. So you can learn something about what the computer is doing through audio channels as well. So these sort of general class of problems are things we refer to as side channels in computer security, because they're sort of revealing information in ways that weren't the main channel that the designer was thinking about. All kinds of leakage shows up in real systems. One sort of other thing to keep in mind is that this leakage doesn't necessarily need to sort of emanate from the computer system right away. So here I'm talking about maybe right away some information is encoded in the radio waves emitted by the computer or in the power consumption. Could be more subtle. In particular, it might be that while the system is running and processing your request, it somehow affects the contents of the cache inside of the computer system, and it's not observable to the adversary yet, but as we'll see, this might in turn make it possible that the information about what's in the cache, which was affected by the key, will in turn affect something the adversary can observe through timing of later operations. There's many ways in which these side channel attacks manifest themselves. So maybe to make this slightly less abstract, let's talk about concrete side channel attacks that people have discovered over the years and what they look like. So the earliest example of side channel attacks actually showed up from the military space. It's a attack that the military called Tempest. This was a vulnerability in old displays, CRT displays. And what was discovered was that if you had a computer system displaying some sensitive document on a screen or sensitive information on a screen, the screen worked by shooting electrons at this sort of large grid of pixels in front of the user. And shooting these electrons emitted a lot of RF spectrum in doing so. And as a result, you could sort of have an antenna that's, maybe tens or hundreds of feet even from the monitor, and you could just sort of watch for the intensity of the electron beam being emitted, and you could reconstruct the image on the screen by following along with the radio frequency emissions of the monitor. So this was the at this point, probably 60 or 70 years ago, that people discovered this problem, and that led to a whole sort of family of standards for how much lead to put around sensitive computers to shield from various emanations from it. So that's one kind of a side channel attack. The sort of maybe more modern examples is in smart cards. If you have some little device with a chip and a cryptographic key that is going to be used for signing operations, maybe you want to keep that key private, like in a U2F device that we talked about before, other kinds of embedded devices that Galen talked about last week. Well, one common way to extract secrets out of a smart card is through power analysis. And the idea with power analysis is that your CPU is going to be running some code implementing a crypto system, and it's going to be dependent on the key. And oftentimes there's some difference on what the CPU is executing depending on what the key is. So you might execute like an add or a multiply instruction depending on whether bit I of the key is 0 or 1. And it might be the case that the amount of power needed to execute a multiply is visibly different than the amount of power that a chip consumes if it's executing an add instruction. And if you have a very fine-grained scope hooked up to the power lines of a chip, you can monitor how much power it's using at any given millisecond or microsecond of time and be able to infer what the CPU is doing, even though it's not trying to expose that to you by design. So power analysis attacks are pretty powerful in terms of attacking and learning secrets out of an embedded system that you physically control. There's a lot of work that has happened in the research community and in engineering and practice, how to defeat power attacks and so on. Another sort of maybe side channel that's more sort of easier to see is in browsers. Your browser has a page cache of recently visited pages, and you can actually use timing in JavaScript to decide whether a user has visited some page or not by loading an image and seeing how long it takes until the browser says the page layout is finished or something like this. So there's information you can learn about a user's browser through timing attacks that you might not be able to learn through directly invoking various browser APIs. And then sort of getting closer to the kinds of attacks we are looking in this paper, in Linux, there's actually a subsystem called dmcrypt. Well, it still exists, but the subsystem was used to encrypt the contents of disks on the fly. So when you write data to a file system, the kernel will encrypt it for you transparently. And the implementation of the encryption scheme in dmcrypt actually had a really serious weakness where there was a CPU cache timing attack which allowed users in Linux to extract AES keys out of a kernel in less than a second through timing of various cache operations. So we'll look at this in a little bit of detail to understand what these attacks look like. Make sense? This covers, hopefully gives you some sense of what side channel attacks look like. Any questions about this and why you might worry? Make sense? All right, so we'll try to build up to the Spectre attack that you guys read about in today's reading. It's a pretty sophisticated attack. It's hard to understand. There's a lot of moving parts. So we'll try to build up to it in a couple of steps. So one thing that's really important to understand the way these Spectre attacks work is the idea of cache timing. So we'll look at that first and try to understand how cache timing attacks work. We'll look at this example of the Linux dmcrypt vulnerability as an example of just like a purely cache timing attack to see what that side channel looks like. And the other thing that Spectre attacks rely on is the use of speculative execution in modern processors. And that's a tricky detail. We'll look at this. We'll look at the meltdown attack in particular as an example of something that just depends on speculative execution. And this is the dmcrypt attack. We'll look at that. And then finally, the last sort of part of the puzzle for Spectre is branch prediction. And with all three of these components, finally, we can hopefully understand or sort of see in detail how these Spectre attacks work. So that's sort of the plan. We'll look at cache timing, then speculative execution, which gives us meltdown, and then sort of branch prediction will give us, with all three components, this whole spectre plan. Make sense? Questions? All right. So let's look first at cache timing attacks and try to understand what's going on there. So what's the setup for this Linux dmcrypt system that was attacked? So the setup is that you might be running Linux on your machine, and you have some user space process running on top of Linux, and the application might call write to write some data to the file system. And the kernel, of course, has a disk somewhere that it's managing. But what dmcrypt does is that it takes the data written by the user and actually calls encrypt on it with some key that lives in the kernel, and then writes the encrypted data to disk. And the key that is passed here should only live in the kernel's memory. User space applications shouldn't be able to get this stuff. They should be able to read and write the data, but they shouldn't be able to get the key to decrypt all the contents of the disk later on. Make sense? So that's sort of what dmcrypt is doing. And just to sort of get you thinking about what the attack is going to do, the attack is going to somehow allow our Linux application to figure out what the key is inside the kernel without the kernel literally printing it or giving it to the application through any syscall. So in order to sort of see how this timing attack might work, it helps to understand how AES is implemented, because that's really the thing that turns out to have some weakness here. So here's what an AES implementation looks like, typically. So we have some key, K. The first thing that AES does is actually takes this key, this is your AES encryption key, actually expands it out into a fairly large array. This array is like, I forget, maybe like kilobytes in size, so a fairly large array derived from a fairly small key. The key is on the order of like 128 bits or 256 bits, and then it expands it out into this large thing called the key schedule. And then if you actually want to encrypt some data with AES, you take some data, you feed it into the encrypt function, and the encrypt function is going to sort of fetch various elements out of this key schedule in order to actually do the encryption. And it does it in a loop. So roughly speaking, you take a byte of memory, and then you take something out of the key schedule, you XOR the byte of memory with the key, you get, the next byte, B2, and then you look up roughly something in the key schedule based on the byte that you just encrypted. So this is what I'm trying to illustrate is that this encrypt function is going to do multiple fetches. It's going to access many elements in this key schedule array, and these accesses are going to depend on the data being encrypted and the key itself. So you take the data, sort of XOR it with some part of the key, you get another byte of data, then you use that byte to look up into this array, you get that byte of the key schedule, and then you iterate from there. So the access pattern into this key schedule array depends on everything going on here, both the data and the key itself. So this is what's going to be kind of part of the weakness here, which is that if we could figure out what the access pattern is to this key schedule, we can use that to infer what the bytes of the key were that caused the implementation of encrypt to access these memory locations. In particular, if we know the data that's being encrypted, then the only mystery to us is what was the key that was used to index into some memory location. And if we know the memory location that was chosen, we learn something about the key. And the data here is actually known by the adversary. So we know what data we wrote. As a result, we can use that to sort of figure out the key. Does that sort of make sense? Questions about what's going on? All right. So we're not explaining fully the details of AES. There's quite a bit more structure going on there. But for the purposes of this attack, all we really care about is that there's sort of a large array of really sensitive material, and even accesses to this array reveal something about the key. So that's sort of dmcrypt. dmcrypt uses AES. The sort of last piece of the puzzle for understanding these cache timing attacks is to understand a little bit about CPU caches and what a CPU cache looks like. So in pretty much every modern CPU, you're going to have a CPU paired with a fairly large cache data structure to compensate for the fact that memory accesses are expensive. So this cache is going to live right on the silicon die of the CPU, and accessing this cache is going to be way faster than accessing the DRAM memory sitting somewhere on the side. So what does this cache look like? So the cache, in some sense, is just a large table, and it's got basically two columns that we care about. There's a column that says, here's the address that we're caching, and here's the data that is stored at this address. And this data is going to be a copy of what's really stored in memory. And there's a couple of interesting sort of structural things about this cache that are important to know. One is that the cache caches units of memory that are about 64 bytes long. Depends a little bit on the CPU architecture. Maybe some CPUs are 32 versus 128, but 64 is a pretty common cache line size. So this thing is called a cache line. And this is the granularity of data from memory that the CPU is going to cache on its die. The other interesting question is how we're actually going to find elements in this cache. So when a CPU wants to load some memory location A, the question is, how do we find A in this cache? And naively, you might think, well, let's see if A is anywhere in this cache. That turns out to be, well, that would be kind of nice if we could do it, because then we could find A at any place in our cache. Then we'd be in good shape if we could locate it. But the problem is that finding A in lots of these cache line rows or sort of cells is expensive power-wise, because this cache, has some size n. This could be, megabytes large. So there could be, 10,000 cache lines or 100,000 cache lines even in a CPU's cache. And it would be crazy expensive in terms of power to compare this address to the address stored in every one of these cache lines. It's like 100,000 compares. It's a lot of logic to execute. So what CPUs typically do is they don't actually check for the address being present in any particular location, and instead they use a hash function effectively. They say, well, the cache line for address A could only be stored here in the location A mod n with sort of n cache lines in the cache. That's the size of the cache. And then the only thing you have to do if you want to find if A is in the cache, find its offset mod n, and then see if it happens to be here. If it's equal to this address, good, we found it. Otherwise, we missed, we got to load it from main memory. Make sense? Hopefully this is a review of stuff you've seen in like 004 or something like this. But any questions so far on any of this setup? Feel free to also ask anonymous questions through Kevin. Yeah? Yeah, so this is how caches work. How we're going to exploit them is, of course, going to be a little bit different. So we have to understand this is what the CPU does, and then in order to actually take advantage of some of these properties, we'll have to play a couple of games here, indeed. Yeah, absolutely. Other questions? All right. But yeah, indeed, good point. So like we can't... This data structure lives inside of the CPU, but somewhat importantly, the CPU doesn't let you just like say, oh, I want to know what address is here, or I want to know what data is here. I don't care what the address is. This data structure is accessed in very stylized ways, and the CPU isn't intending for the software to be able to just like go and say, oh, yeah, I want this thing. It's used by the CPU, and we can sort of cajole the CPU into, taking advantage of the fact that this thing exists. So let's look at how this AES cache timing attack worked. So I should say, regular timing attacks, like this attack we're about to describe on sort of AES implementations, these things have been known for a couple of decades by now. The specific attack on Linux is dmcrypt. A couple of researchers wrote a paper about this thing close to 15 years ago at this point. So these things are fairly well understood, and we know how to deal with them. But they're sort of a building block to get to these fancier things like meltdown and spectre. All right, so what's the attack? So the setup is as before. We have the Linux kernel, and we have our adversary running on top of the Linux kernel. And if I want to figure out what the key is, what I want to do is first, I want to fill the cache. So how do I fill the cache? Well, I'm just going to load lots and lots of memory locations so that the whole CPU cache is going to contain locations that the adversary loaded. The whole cache is full of adversarial, adversaries' address locations. As a result, nothing else is in the cache. The cache has nothing else except for adversaries' data. So once we sort of fill the cache with all of the adversary state, then the next thing we're going to do is issue a write to the Linux kernel. This write is going to go into the kernel, and the kernel is going to encrypt this data for us with the AES key. And as part of this encryption, the kernel is going to run the AES implementation that's going to touch that sensitive key schedule. And as part of touching the key schedule inside this encrypt function, some memory locations for this key schedule are going to get loaded into this cache. Remember, the cache used to contain all memory from the adversary from the step 1. But then the kernel filled in a couple more locations with its own data from the key schedule. Now, the kernel certainly wasn't trying to expose which locations in the key schedule it was trying to access, but now the adversary can figure this out. And the way the adversary figures this out is that the adversary is going to time how long it takes to access all of its memory. So, roughly speaking, after the write syscall, we're going to access all these same memory locations that we used to fill the cache. And for each memory access, we're going to record how long that memory access takes. And if it's fast, then this means this location was not evicted by the kernel. And if the access is slow, this means that that particular memory location was evicted by the kernel, and in particular by encrypt. So now, what we've done is we used the CPU cache and using sort of timing of loads through the CPU cache to figure out what was the footprint of the encrypt function in the OS kernel that ran in response to the write syscall. Does this make sense? So now the adversary knows exactly what sort of positions in that key schedule the kernel's encryption function touched. And now there's sort of something I'm not describing here in a lot of detail for you guys because we haven't talked about the internals of AES. But as I hinted before, the internals of AES are pretty sensitive in terms of the locations in the key schedule that you access. And it turns out that if you can learn which locations in the key schedule you're accessing, then you can figure out, then you can sort of slowly guess the key one byte at a time, roughly speaking. And this turns out the security researchers actually implemented this attack. They were able to extract the encryption key out of the kernel in, 60 milliseconds or something super fast like this. It's an incredibly high bandwidth channel given the size of the key. Yeah, question? Okay, so doesn't this rely on other processes not getting in your way? So you're absolutely right. Many of these side channel attacks, actually, like this whole family of side channel attacks is a fairly noisy game you're playing because it's not like someone is like sending you data error corrected and like, oh, I absolutely know what the data was sent. So in pretty much all these side channel attacks, we're going to be trying to pick up some signal like, what was in the cache? And there's going to be quite a bit of noise involved. So you might need to repeat the same measurement multiple times. So if there's other processes running, what you might do is you might do this fill, write, time combination a couple of times. And the signal should be the same all the time because the same key is going to have the same memory access pattern and you should see the same result. But if something is varying, well, that's probably some kind of noise. There could be lots of noise. There could be other processes. There could be like an interrupt that happened. Maybe there's something else that showed up in the cache. Who knows? Lots of reasons why you might have sort of noisy readings here. But the thing to keep in mind is that for pretty much all these side channel attacks, repeated runs average out the noise but keep the signal. So you can amplify most of these side channel attacks by just running it multiple times. So in fact, in this case, the signal on an idle Linux machine was strong enough that these guys could exploit it in a very short amount of time. Probably if the machine was loaded, they might have to average or play some other games to make sure they can get a clear reading. But you're absolutely right. I think keeping in mind, this is a situation where you're really trying to, it's a very probabilistic game we're playing here. Yeah. Other questions, comments? All right. So the point of this example was to really give you a sense of what it's like, or what can you do as an adversary by timing the cache accesses. And what this sort of showed is that, well, it was sort of known by the time this particular attack was developed, but it's actually quite feasible for an adversary to figure out which locations are or are not present in the CPU's cache. And this cache is shared by anything that is running on the CPU. In particular, it's shared by the application, by the kernel. It's shared between applications that run on the same CPU, etc. So it's a little bit sensitive thing to share a CPU with some code you don't trust, because now this code might learn what memory locations you're touching. Make sense? Questions? All right, so that's cache timing. Now let's talk a little bit more about speculative execution and this meltdown attack. So what's going on there? So to look at speculative execution, this is another CPU implementation optimization. So the CPU wants to run faster, and speculative execution is a really powerful technique that pretty much every modern CPU, except for maybe microcontrollers, every modern CPU does speculative execution to get high performance. You guys have probably seen this in 004 or 823 to some degree, but let's walk through it again in case you haven't or if you've forgotten to understand really what's going on. So there's two things going on with speculative execution. One is there's a stream of instructions that the application developer wrote. And the application developer is expecting these instructions to run as if they're running one at a time. Otherwise, it's sort of hard to make sense of what the hell is going on the CPU. So there's sort of this linear stream of instructions on one side. Like you might have instructions like add R1 and R1 and put the result into R2. Maybe then we have like a move from some address A into register R1. Then maybe we have another add, R2 plus R3 goes into R4. Maybe then we have another move, load R1 and put the result into R5. Anyway, some kind of stream of instructions. So from the perspective of the person that wrote this code or the compiler that generated this assembly code, the CPU should run one, then the next, then the next, then the next. And the CPU tries and for the most part succeeds in providing this illusion that these instructions ran one after another. But there's a lot of sort of opportunity to do faster. So if we sort of naively think of what's going on when these instructions run, so what we're going to draw sort of an execution diagram with time going to the right. So this is a different way of looking at the same instruction stream. From an assembly perspective, they run one after another, but the CPU has many instructions running at the same time, and it's trying to play this game of making it look like only one ran at a time. So you might have this add instruction running, and eventually it commits, but while the add is executing, the CPU would like something else to do. So for example, it might want to start loading, or like fetching this instruction from memory. Fetch the instruction itself, decode the instruction, then maybe actually do the memory load, then maybe validate something like permission checks. And then after all these steps complete, maybe you'll actually commit this instruction. So what I'm describing is sort of out-of-order processor execution, where the processor considers many instructions at the same time, and for each instruction, the instruction could be in many possible states. So this instruction might be just fetching the instruction opcode itself, or it's decoding it, or it's figured out that it's a move and it's loading the address A from memory, or something else, and so on. But, okay, once we've started running this move instruction that loads A from memory, this instruction might run for quite a while. In particular, if address A is not in the cache, this is going to take hundreds of cycles to execute. because accessing DRAM could easily take 100 cycles. So we'd like the CPU to do something else. So what the CPU does, it actually starts fetching the next instruction. Also it fetches, decodes, execute it in the ALU, and eventually it commits it. Now, here's the thing. We can actually commit this instruction before we know what happened to the previous instruction. Because it might be that this previous instruction hit an exception. Like it could be a page fault or some other kind of a problem that causes this instruction to raise an exception, and the second instruction never runs, or the third instruction never runs. So this instruction might have finished executing, but it sort of has to hang around and wait for this previous instruction to commit until this next guy can actually commit. In the meantime, we got these two guys running. CPU needs something else to do. It can actually start fetching the next instruction as well. And also fetching, do a memory load, etc. Make sense? So this is how out-of-order CPUs work. Hopefully for many of you guys, this is review. I guess there's two things that are maybe salient to our meltdown attack that I haven't mentioned here yet. One is that, of course, we are speculating, this is what speculative execution is talking about, that we will execute these instructions eventually, but it might be that our speculation was wrong. So it might be that this instruction, the move address A into R1, this might hit an exception, in which case we need to undo this instruction even though we started executing it. So typically CPUs might say, well, instead of committing it, we're actually going to abort this instruction and undo all the changes. So this instruction might have already almost modified register R2 with the result of might have modified R4 to have R2 plus R3. But if it turns out this instruction hits an exception, we'll undo this and put R4 back where it was. A lot of fancy machinery in the CPU to actually make this happen. And the last tidbit that turns out to be relevant is that sometimes the CPU will actually even forward values between instructions that are speculatively executing. So in this example here, we have this instruction that loads R1, and this instruction reads or uses R1 to in turn access another memory location. And the CPUs, like Intel and AMD CPUs, are fancy enough that they can actually forward the tentative value of R1 from one instruction down into the other instruction, while they're all sort of speculatively running. And if all of our guesses turn out to be right, we'll commit all of them, as if everything was running super fast. But then, if it turns out we were wrong, we'll abort. So I think that's all the machinery we need, roughly, to understand this meltdown attack. So before we dive into the details of the attack, any questions on sort of CPU speculation and how this works, what's going on? It's going to be important in a second. All right, clear enough. You can ask questions later if need be. All right, so let's try to understand how meltdown is going to work in our case. This meltdown attack that the paper talks about. So this uses sort of speculative protection checks, or takes advantage of the fact that in some CPUs, or many CPUs, Intel, some ARM CPUs even, some AMD CPUs, part of the thing that happens when you're executing a memory load instruction is that, well, of course we need to load the value, but we also need to do a permission check to make sure that this address is accessible to the current process. That in particular, it's not a kernel memory address, but it's actually accessible to user level code if we're running in user level. So here's what happens in a meltdown attack, or what could happen in this vulnerability. You're running on some kind of an OS kernel, and there's some secret in the kernel that you want to read. Like maybe there's some kind of a cryptographic key in the kernel that you really want to access. Kernel doesn't expose this. But what you're going to do in user space is you're just going to sort of figure out what the address is of this key. Maybe it's an address that's well known. Maybe you figured out this address with some other means. But anyway, you have an address of some secret data in the kernel you'd love to access. The kernel doesn't let you do it, but you're going to use this speculative execution to somehow be able to do this. And we're running adversarial code in user space. So how's this going to work? Well, what we're going to do is we're going to load the address at address A into some register R1. And normally, this shouldn't be allowed. Address A is only kernel memory. The CPU will give us an exception and will stop the execution of this instruction. We'll never get the value of R1 here. We'll never know what this was. Except, here's the thing. what the adversary can do in their code is do this move, and then right after this move, it can do a move of some array in user space of R1, and I don't know, load it into R2. Doesn't really matter what we do with it. And what's going on is that the user has some kind of an array they have. This is their array. And this array is going to work basically like this timing attack, this cache timing attack we looked at in the AES vulnerability 10 minutes ago. So how is the CPU going to execute these instructions? So as before, right, the CPU gets the first instruction and starts executing it. Here's the execution time going forward. Well, the CPU is going to fetch this instruction, and it's going to start the load of this memory address A. And this load might take some time. Then the CPU is going to do some protection checks. And then eventually, it's going to commit the instruction and either allow it or jump to the kernel with an exception. All right. In the meantime, while this first instruction is executing, the CPU is going to start running a second instruction because that's what it does for performance. So it's also going to fetch this instruction, and then it's going to try to load this array offset by R1. And R1 is coming from the previous instruction, so we have to wait for the load until the value is available. The value is coming from the previous instruction, but as soon as the previous instruction gets the value of R1, we can forward it to instruction 2 and start the load. And now this instruction is loading an array of R1 into the cache, and eventually it's going to do its own protection checks, etc. These protection checks are actually going to be okay because we're just accessing an array of R1. This is totally a thing that the application is allowed to access. Of course, what's going to go wrong, as you're probably seeing, is that this first instruction is going to hit an exception because this protection check is going to fail. So in the CPU terminology, this instruction will commit, but the next instruction to execute isn't actually the second move. The next instruction to execute is kernel code to handle the exception. So we were wrong to speculate that this was going to be the next instruction to run. So the CPU eventually aborts the second instruction and instead starts running the kernel exception handler. But what's happened is that we managed, in the meantime, to access an array of R1. And we don't know what the value is of this thing. We don't really know what R1 is either. But the sort of subtle thing is that the cache contents is now modified as a result of this speculative execution. So the CPU tried to roll back the side effects of running the second instruction because it realized that it shouldn't have run the second instruction. But it turns out that pretty much every CPU implementation does not roll back the changes to caches because the CPU designers thought the cache is just an optimization. It doesn't really matter what's in the cache. Even if you put it in the cache, it was allowed to be there. It's okay to leave it there. So this is sort of the crux of what's going on with these speculative execution attacks, which is that the side effects of speculative execution are not undone fully. And this one exception to how they're not undone is the contents of caches are still there after the speculative execution machinery rolls back this incorrect guess. Does that make sense? Questions about this whole machinery? As you can sort of see, this is like a fairly involved attack that involves, cache timing, lining up, guessing the address of some variable in the kernel code, etc. A lot of tricky stuff going on. But, okay, how do we finish this attack now? Well, we just run these two instructions. We get a page fault because we weren't supposed to handle address A. But once we hit the page fault, we can ignore the page fault, and now we will perform this cache timing analysis to figure out which array offset was brought into the cache. So if we know which array offset was brought into the cache by this speculative instruction, we can figure out what the value of R1 was, even though we weren't supposed to have access to R1. So in this way, we can almost not quite directly, but fairly reliably read the contents of arbitrary kernel memory, even though the CPU doesn't allow this directly. Make sense? Questions? Yeah? Okay, so your question is like, where would we get A from? Yeah, that's a good question. So, might be that one thing that often happens in kernels is that a kernel probably maps all of physical memory somewhere to an address space, because at least traditionally in kernel designs, it's been convenient to be able to access physical memory just directly. So one thing you could do is, you probably know by design, like Linux maps physical addresses at this 64-bit address. So if you have a physical address of memory that you want to access, you can just compute it and go access physical memory that way. It might be that you can use this to access some well-known memory locations, like maybe some I/O devices are right there. You can access those if they're cacheable. You can access the contents of the screen, like VGA memory is right there, also in physical memory. It might be that you have the address of some kernel data structure or kernel code. You could, if you get that maybe from some KSLR leak or who knows what, then you can access this. So this is not a full attack. Like, this is not a command you just run and like it dumps you the key. You have to find the key. But that was a big deal, right? Like before, if you just sort of knew the kernel address of some secret key, well, you still couldn't get it. Maybe you could exploit a buffer overflow and you could mitigate some address space layout randomization if you knew a kernel address. But this makes it a much bigger deal to know a kernel address. And plus, you can like scan kernel memory now. You can see which locations are even valid by guessing which ones have non-zero contents. And you can sort of scan and see which seems to, you can do a lot of guessing by looking at random memory locations. So you're right that I think in a lot of these side channel attacks, in the papers we read, the papers are really not sort of retrospective analysis, all like, oh, how did we get compromised and let's understand what the attacker did. These are really more descriptions of a one step in an attack that you might worry about. And that's why, like, even in the Spectre paper and this meltdown analysis paper that we assigned for you guys, like, there's not a full attack that someone would execute from, like, hitting a command to something bad happening. That's really showing that something surprising is going on that you thought shouldn't happen. And along these lines, I don't think these attacks have really been used broadly to attack anything in practice. It's more that this is a really worrying thing that people realize, like, holy cow, this is bad. Could be part of a bad thing. And as a result, that's why people are trying to mitigate them. Not because, lots of money was stolen using these attacks and now we have to patch them. Yeah. Question? Yeah, so there's sort of two parts to that answer. One I can describe. One requires a lot of details of AES that I cannot describe in this sort of time frame. So the way, there are sort of two steps. One is if something in the cache is evicted, the reason it's evicted is because the encrypt code accessed the memory location. And the CPU went and evicted the thing that was there before and put the part of the key schedule in this memory location. Now, that's the part that I can explain. The sort of other part I can also explain is once the application, the adversary's application starts running again, it can measure how long it takes to access every one of its own memory locations. Some of them are going to be fast. The reason they're fast is they're still in the cache. Some of them are going to be slow. The reason they're slow is that something else went into that memory location. And when you know that it was slow, you know that something with an address of a mod n equal to your thing got put in that memory location. So it's the fact that these memory locations, or these cache slots are indexed by address mod n. That's what lets you figure out. If I know my offset 55 was evicted, that means that your key schedule was accessed at offset 55 as well, roughly speaking. And that gets you. And then there's some, details of how AES is implemented that gets you from knowing which key schedule offsets were access to which key parts, what the key was. That I can't explain in the remaining time, unfortunately. Yeah. Question? I'm sorry, I didn't hear. Can you say again? Yeah, okay, so all these attacks, as I mentioned, right, they're quite worrisome, not necessarily because anyone exploited them directly, but because the kernel developers, hardware developers, they look at this and say, well, this could be bad. Like, if we do nothing, then it's going to be potentially a disaster. Might not be. Might be that, like, they're really hard to exploit, and, they are tricky to exploit, but not worth risking. Let's try to figure out how to mitigate them. So the mitigations are quite different in every setting. So, for example, for cryptographic code, like this cache timing attack that I talk about with AES, there are sort of two defenses that people play. One is that most CPUs now have hardware implementations of AES, where this key schedule thing isn't actually a software thing that lives in the cache, but it's like part of the CPU itself. There's a special instruction to do some AES step, and that has no cache footprint, doesn't leak any information. Another thing that people do in cryptographic implementations to avoid these kinds of cache line timing attacks is they make sure their implementation has predictable memory access patterns. So the thing that is sort of a big no-no in cryptographic implementations is key-dependent memory accesses. So that's exactly what we had here. Pretty much every modern implementation of any crypto scheme, like elliptic curve crypto, etc., they're extremely careful to make sure that the memory accesses they access are not dependent on the key and usually not even on the data itself. So that you could publish the addresses accessed publicly, and that wouldn't compromise any security at all. And once you have that mindset, then no problem. Cache timing attacks aren't a problem. Now, how do people mitigate these meltdown attacks? Well, there's sort of a couple of things people have tried. One is that the hardware manufacturers actually released new hardware that changed the speculation behavior somewhat. So one thing you could imagine here is that maybe we should really put the production checks first before we do the load. Something like this, like first speculate in the production checks, and then if that passes, then do the load, or at least do them concurrently. Or maybe don't do this forwarding of the loaded value to later instructions until the protection checks come back clean. So there's like subtle changes to the speculation behavior that the hardware manufacturers can make and have made to make these attacks more difficult or impossible to pull off. There's also software mitigation. So existing hardware didn't have these hardware changes. It had this behavior that was buggy, or I don't know, vulnerable. I don't know if buggy is the right word. There, Linux developers actually constructed careful sort of tricks in their kernel implementation to make these attacks difficult to pull off. So what Linux does actually is traditionally there's sort of one page table for the combined process where the kernel code is mapped but not accessible at the kernel's addresses. And it's this protection check of not being accessible that the hardware screws up in a sense. So modern versions of Linux on especially vulnerable hardware, older hardware, they actually maintain two page tables. One while running user space code where almost none of the kernel memory is accessible. And then when you make a syscall, the first thing the kernel does actually changes the page table. And then you can run the syscall. But as a result, if you just do a memory access while in user space, the hardware is going to just hit a page fault because that memory is just not in the page table at all. And the protection check doesn't matter. So there are some tricks that the kernel can play to mitigate this. There's a whole bunch of tricks people have come up with for mitigating these kinds of side channel attacks. Some of them are quite subtle. But yeah, that's the question. Okay, so your point is, okay, so like how does this two-page table thing work for mitigating meltdown? And what you're observing is that you have to have some kernel code mapped because when a syscall happens, you got to start running kernel code. You got to run something there, man. Something's got to be mapped to start running it. So what the Linux developers do is they leave just a little bit of code mapped that handles the syscall or page fault or exception, and a little bit of kernel memory mapped, like the initial stack needed to start handling the exception, but everything else is not mapped. So the only thing that's in the page table while the adversary's code is running in user space is some minimal amount of stuff needed to switch page tables, but none of that is secret. So that's okay to leak. You might be able to indeed leak it still through Meltdown, but it's not a big deal. You know what the contents is. Like the code to switch page tables, you could have just gotten it from a Linux source. You don't need to run this attack. And all the secrets, potentially, are in this other page table that was not present while you're running the adversary's code. Makes some sense? Questions? All right. So this is the sort of simpler one of these speculative execution attacks. Meltdown, it sort of just depends on this one sort of weird bit where the processor is speculating on the protection checks and allows this data to be forwarded to later speculative instructions before the protection checks succeed. So now let's try to make sense of the sort of full Spectre attack. The only thing we haven't talked about that turns out to matter for Spectre is branch prediction. So let's talk a little bit about branch prediction in CPUs and what's going on there. So in CPUs, you might have code that, I don't know, compares two values and then needs to check if they're equal. Well, if they're equal, we're going to branch to some location like foo. So there might be, the next instruction to run is, I don't know, add R1 plus R2. But if R1 was equal to R2, we'll branch to foo, and this is, I don't know, some kind of a subtract. Who knows? We have an if statement, basically, in assembly code. So the CPU wants to get high performance by doing this kind of speculative execution of running multiple instructions at the same time. But in order to do this, it needs to know which instructions to even try executing. And branches make this difficult. So you might have a situation where you run this compare instruction, and I don't know, you start loading fetching the instruction, then you do the ALU operation to compare them. Who knows, eventually you commit. But in the meantime, you got to start running the branch. So, we'll of course fetch the branch, but then we're stuck. We don't know which way to go. So the CPU has a branch predictor. So branch predictor is this sort of a funny data structure. It has a guess of whether this branch is going to go this here or here. And the way these branch predictors work, roughly speaking, is that it's kind of a function of the sort of jump address. And this function basically says, is this branch taken or not taken? So the CPU has some data structure implemented in hardware, kind of like a CPU cache, but much smaller. And it has some dynamic, set of guesses, some statistics it keeps about branches in order to be able to implement this guessing function. And as sort of the signature suggests, most of these branch predictors try to make the guess dependent on the location from which you're supposedly jumping. Like the address of this BEQ instruction in memory, that's sort of the key into the branch predictor. And then for that address, the branch predictor is going to build up some history. Are we typically branching here, or are we typically branching there? So the branch predictor is going to tell the speculation machinery, I don't know, maybe let's say it's not taken. So typically, then it'll start fetching this instruction and trying to execute that. And hopefully our guess works out well. And if the branch predictor is accurate, we'll be able to commit all these things and get high throughput. But if it turns out that our guess was wrong, we will instead abort this guy and instead start fetching this other guy. So if we were supposed to branch, but we didn't in speculation, well, we've done all this work. Too bad for us, but we have to abort. Then we start fetching the real thing we should have run. But notice, right, it takes quite a bit longer to do so. So there's a performance penalty for misspeculation on the branch. Make sense? So this is branch prediction, important performance optimization, as with speculative execution as well, but turns out to be a big deal for these Spectre attacks. So any questions about branch prediction? Yeah. So the instruction of the branch that's not taken, like this add instruction, like if we thought we were going to run this add, but then it turns out we don't run it. Yeah, so this thing was running in our CPU, but it was running with the support for speculative execution. So the whole thing was super conditional. Right? It might have already effectively modified R3 because it thought that it was going to happen, but the CPU is tracking enough stuff that it can actually abort it and can say, we modified R3, we could have run lots of other instructions. All this stuff is carefully tracked. So if the branch predictor says, shoot, we screwed up, then all these instructions can be undone, and then we'll start running the real thing instead. They don't get, I'm sorry. They get undone, yeah, so they don't, I don't know, deleted or not, but they get aborted. It's as if they never ran. So we basically, it's as if the CPU did something useless for like, some microseconds, and too bad. Or some nanoseconds, I guess is the right scale. But yeah, like we wasted, I don't know, 10 nanoseconds doing something not useful. We aborted it, but now we know what to do. Now we're running this thing. Okay, we had a pause. That's fine. And again, as before, the one thing that's not undone is the cache contents. If during this speculative execution, as a result of a branch prediction, we happen to have tried to access some memory locations, the CPU will bring them into the cache, but it will not kick them out of the cache if it turns out we misspeculated. So again, that's sort of the one source where we can get some data out of a speculative execution block or a branch prediction block. Make sense? Any other questions about branch prediction? How that works? All right. So now let's try to put together the spectre attack that the paper talked about. It's going to sort of combine all these things we've talked about so far. All right. So, spectre attack. This is the V1 attack that the paper talks about, sort of the base version of this branch prediction thing. So, all right, what's the setup for this attack, or what's the sort of imagined scenario? Well, probably the most simple scenario to imagine is the same setup we were talking about with the meltdown attack. So we have some user space code running on top of a Linux kernel, and again, there's some sort of maybe a key that lives in the kernel that we'd really like to read, but we can't. So the way we're going to do this is through the spectre attack, and the spectre attack relies on the presence of something called a gadget, some code sequence in the kernel that we're going to take advantage of. So the setup is the user is able to pick some value I and pass it through like a syscall to some function in the kernel. We'll call it victim, or this is the gadget, and it's going to work on this value I. So what does this victim look like? Well, it's basically going to have a bounds check on I. So this is a fairly common thing to see in Linux code. So we'll say, yeah, if I is less than the size of some data structure, of some array, well, we're going to access the value of some array of offset I. This is a pretty standard thing to do in the Linux kernel. If you want to allow the user to index into some data structure, well, you bounds check it first, then you access the array. Then sort of the one subtle thing that needs to happen in order to make this gadget work for the spectre attack is that then we need to access another memory location with this value v. So you might need another statement here that accesses another array, like array 2, of value v. All right, so this is the kind of style of code, right? Like, it doesn't have to be literally this. There could be other instructions or lines of code in the middle there. But this is kind of a gadget that this spectre attack is able to do. And you can probably see some similarity with the meltdown attack that we had before. This is going to be really a move instruction that loads from, roughly address I into R1. And this basically moves, some array or array 2 here of R1 into R2. There's the same pattern that we saw before, but what's going on here is that the kernel was trying to be careful. The kernel was trying to make sure that you can only access legit offsets, legit values of I. So if you try to access a value of I that was like way out of bounds, the kernel was trying to not do this. But turns out that speculative execution gets in our way, and the speculative execution machinery in the CPU might run this code in the middle anyway. And now, this code can leak the contents of this memory location that's past the bounds check through the same machinery that we looked at in this meltdown attack. So let's try to step through this maybe in a little bit more detail. So first, any questions about sort of this overall plan? Yeah? Yeah, so we somehow need to make sure that the CPU branch predictor thinks that this branch should go inside the if statement. So the attacker's job is going to be first to actually massage the branch predictor to do it that way. Then we need to make sure that somehow this branch prediction doesn't resolve too quickly. So if the CPU figures out right away that I is not less than size, it'll not even bother speculating inside the if statement. So you need to make sure this takes a while to execute. So what you need to make sure is that the size variable, make sure the size is not cached. So if the size variable is not in the CPU cache, then this if statement is going to take it forever to run. It's like hundreds of cycles to load the size variable out of the DRAM. In the meantime, the branch predictor was carefully massaged to say, go inside the if statement. Now, we're going to run the code inside the if statement, and then we're going to use this sort of cache timing attack style to get this array2 of R1 into the cache. And that's sort of the last part of the attack, effectively. Now we're home free. The cache has been modified so that this sensitive value is the offset that happens to be in the cache now. Now the CPU can catch up, invalidate this whole branch, do whatever it wants, then get back to user space. Now we'll do a cache timing attack, figure out which thing went into the cache. Then we'll figure out R1. R1 was this out-of-bounds value we weren't supposed to read. So that's roughly the sketch here. Make sense? Other questions? All right. So one thing I thought we could do is actually look at the code for this attack that the original developers of the Spectre paper put together. So let's see if I can get my projection to work. Had some funny thing going on before, so let's see if this works. Maybe? Oh yeah, that kind of works. All right. So here's the code for the Spectre attack that you guys looked at in the reading question. So there's a couple of interesting things here. One is, this is sort of a funny looking attack. It doesn't quite look like the setup we had in the attack I described on the board. On the board I was saying, we would have an attack where the user is trying to read some sensitive stuff out of the kernel. Instead, there's really sort of many different settings in which you might worry about a Spectre style attacks. So here's sort of the different settings in which you might worry about this. One thing that we talked about is indeed, so user tries to find a gadget in the kernel. So that's one style of attack that we talked about. Another style of attack that the sort of demonstration proof of concept code is trying to illustrate is a different setup where actually none of this is in the kernel. It's really just all in the application. We have one application running. Let's imagine this is maybe your web browser. And what's going on is that inside the web browser, there's many protection domains. What I mean by protection domains is that there's sort of the web browser itself. It might have some secret data. And the web browser is running code that it doesn't fully trust, like JavaScript or WebAssembly. So there might be JavaScript or WebAssembly code. And this WebAssembly code can actually invoke this gadget inside the browser. And the WebAssembly code is sandboxed, as we looked at a month or two ago. It's sandboxed properly, but it's able to call out into some helper functions in the browser. Those helper functions might correctly do bounds checks, but those bounds checks might be bypassed by speculative execution, allowing this JavaScript or WebAssembly code to infer the contents of memory locations past the end of that array that it's not supposed to read. So that's sort of the setting that this attack code is trying to, suggest or, emulate, if you will. And in this setting, actually, Spectre attacks turn out to be much more difficult to mitigate, where they're sort of where you have some untrusted code running inside your browser and your process, like JavaScript or WebAssembly. Spectre attacks are kind of annoying to deal with there, maybe more so than in the user to kernel setting. So anyway, here's a snippet of sort of the imaginary victim code. So here's roughly the victim function. This is the gadget. It does pretty much what we were drawing out on the board. It takes some argument x. It tries to do a bounds check on it. If x is less than the array1 size, it loads array1 of x, and then it loads array2 of that location times 512. So there's a couple of subtle things here. One is that it actually needs to multiply the value it gets from array 1 by 512. And the reason for multiplying it by 512 is to basically make sure that we hit a different cache line for every possible value that we're reading out of array 1. So if we just literally took the byte that we read out of array 1 and we used that to index into some other array, then many different values would fall into the same cache line. And then if we learn which cache line was accessed, well, must have been one of the 64 bytes that mapped to that cache line. So the multiplication helps this proof of concept code distinguish between the different values that it's fishing out of array 1. Make sense? So that's one thing that's going on here. The other is that the memory is actually carefully laid out. So these variables, array 1 size, array 2, and array 1, they're all sort of laid out up here. And they're all actually separated by these unused blocks. And the reason for this is so that the array 1 size variable lives in a completely different cache line from the array 1 array itself, so that you can separately evict array 1 size and then separately talk about which memory locations from array 1 are present in the cache. And then the other thing, the array 2 is also padded with 64 bytes. And all this padding just ensures they're sort of cache line separated. And then there's the secret value that sits right here. This is supposedly some secret value you could imagine is maybe like some secret value in the browser that the browser is trying to protect, and that some WebAssembly code is trying to fish out of the browser through the Spectre attack. Make sense? Questions about this supposedly victim code? All right. So then what's going on in the attack itself is that, let me skip down to the main code. What the main code does is it sort of repeatedly tries to read a byte using a maliciously chosen X value. And it uses this read memory byte function that you guys looked at for your reading question. And it just steps this malicious X value from 0 to the length of that supposedly secret string. And in order to read that supposedly secret string, it sort of figures out what should be the X offset to go past the end of the array and read the secret. So the sort of X needed to read the secret is just like the difference between secret and the start of array 1. It's probably, of course, past the end of array 1, but that's okay. We're going to get past that bounds check. So the main code just is going to read one memory byte at a time with these out-of-bounds X values. And then this read memory byte function has basically a bunch of carefully written code to arrange the cache in a position where we're able to sort of clean out the cache contents, run this attack, measure which memory location was brought into the cache during speculative execution, and then figure out which one it was through timing. So there's a bunch of, as was pointed out earlier on, there's a lot of noise in these real attacks, and that's the reason for many, many loops here. So this attack tries everything, 1,000 times, and then tries the inner loop 30 times. Each one of them has sort of 5 runs to train the branch predictor. So this attack actually calls the gadget code 5 times with a good value that is in bounds to get the CPU branch predictor to train on taking the branch into the if statement. And then the 6th time, it passes an out-of-bounds I value. But hopefully by this time, the branch predictor has been trained to say, go inside. And at that point, we'll hit our speculative execution out-of-bounds read. So this is sort of the kind of stuff you have to do in order to implement this attack for real. And even this, right? Like this is not for real. Like this doesn't give me the SSH key of any real machine yet. This is just sort of a proof of concept that something funny is going on. Real attacks will probably have to have lots more details figured out. But hopefully this gives you some sense of what these attacks might need to do. Make sense? Questions about this? So we can actually, I guess, even try to run this. So here I have this code compiled on some machine I'm running. And if I run it, actually, it iterates over all the 40 bytes. And I guess this is the answer to the reading question. The letter T is the answer. It's the first byte of the secret that it's trying to read. And then, goes one by one. The magic words are so and so. So this sort of example is showing that indeed this function, even though it's not ever directly reading this, the contents of this secret array, it's still able to infer it by the effect that the speculative execution is having on the cache. And then it's figuring out the cache timing to figure out which cache location it was actually touched. Make sense? Kind of? Any questions about this so far? All right. So let's talk a little bit about, I guess, the various mitigation strategies and how much we should worry about these speculative execution attacks. So how do we mitigate these attacks? So as I mentioned, for example, in the meltdown case, it's really sort of a combination of two things, meltdown. One is really hardware fixes or firmware updates, microcode updates. So modern CPUs actually accept signed microcode blobs from Intel or AMD. You can download new microcode into your CPU, and Intel actually patched a bunch of these speculative execution vulnerabilities through microcode updates, which was kind of cool. There's also sort of OS workarounds or mitigations that can be used. So I should say there's a whole bunch of different speculative execution attacks that exist beyond just Spectre and Meltdown that you guys read about in the paper. So on my laptop, I can actually look at all the different kinds of vulnerabilities that Linux knows about. So there's just a bunch of them. I guess, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9 that Linux has potentially mitigations for. My laptop turns out to be fairly modern and has a new CPU where a bunch of these guys are just not existing. And basically, Intel fixed them in hardware, and the kernel doesn't need to do anything about these attacks. But for some of them, actually, it's still needed. So for some of these attacks, speculative store bypass, Spectre v1, Spectre v2, which does the branch target buffer attack. There are some mitigations that Linux needs to enable and deal with. But for older CPUs, it's actually much worse. So I can SSH to another machine that is a much older machine. And if I run the same command on this other machine that has an older CPU, you can see there's a lot of mitigations that Linux has to actually implement in software because the CPU hardware is vulnerable to pretty much all of them. I guess maybe not the last two for whatever reason. But anyway, there's a real performance overhead for some of these mitigations. But many cloud providers actually thought it's important enough to mitigate despite the CPU cost. So pretty much Google, Azure, AWS, they all enabled similar mitigations in their virtual machine monitors to make sure they don't accidentally leak data through these side channel attacks. Even though for them it's like a real cost, right? Like their CPUs now run slower somewhat. Probably maybe on the oldest CPUs, you can imagine some of these attacks, maybe 10% CPU overhead. That's a real cost for them. That's like millions of machines times 10%. That's a lot of money lost on extra CPU cycles. So they thought these were important enough to bother mitigating. Now modern processors have made the mitigation cost less because they're implemented in hardware to some extent. But nonetheless, this is a serious thing that is currently under quite a bit of active development. Linux guys are looking at this all the time. Hardware vendors are still trying to figure out how to better address on these. There's new side channels coming out. Endless sort of debate in the security research community what to do with this for the moment. So that's for Meltdown, I guess. We talked about some OS mitigation strategies. For Spectre, things are a little bit trickier. One reason why it's, if you remember, it was easier for hardware to mitigate Meltdown is that roughly all the hardware just needed to do is to make sure the speculative protection checks happen early enough. So that's not a huge deal, as it turns out, to make that speculative check earlier. For Spectre, what you basically have to do is avoid branch prediction in that goes down the wrong path. And branches are everywhere, and branch prediction is absolutely crucial for performance. And it's hard to make some of these branch checks earlier if the branch depends on some value that was missed in the cache. So it's really hard to come up with sort of broad base defenses for Spectre that always work. So what people have done is actually done a whole bunch of different things. One is, some systems try to avoid gadgets. So, for example, browsers or JavaScript runtimes or WebAssembly runtimes, they try to actually generate code so that there's nothing that looks like a gadget that you could possibly jump to. That's like a weird constraint, but people actually tried this approach. I don't know, it seems to be sort of working. Another possibility is actually add instructions. So add a fence to block speculation. So in this if statement, in your kernel code, for example, what you might do is actually add some kind of a fence instruction here that stops the CPU from speculating past that fence. That's like a pretty costly thing because now that code takes longer to run potentially, but this is one thing that Linux does on some architectures. Another trick is to actually change that first memory load. So v equals array of I. One thing you could do is actually replace that with v equals array of I mod size. So that actually gets the CPU to make sure that the offset for the memory access never actually goes past the end of the array. So Linux actually does this on some other architectures as well, depending on what actually turns out to be faster. So that's sort of the set of tricks that languages or sort of kernels do. The other thing that the Linux kernel does is actually flush the branch predictor on context switch. So when switching between two processes, Linux will actually sometimes flush the branch predictor state to make sure the branch predictor training done by an adversarial process can't influence another process that's running on the same machine, so that these spectre attacks are difficult to pull off across processes. Question? Well, okay, so the question is, how do you know which branch is going to be predicted? Well, in this case, the way the adversary did this is by running this branch one way many, many times. Okay, so you're right that, okay, so sorry, so you're saying that even if you don't train the branch predictor, you can still sort of get some value out of this attack because half the time it'll branch to where you want to go. You're absolutely right, like this is not a perfect defense. Many of these side channels have these unsatisfactory defenses where, well, you make the attack harder to pull off and, so you're absolutely right, yeah. So it might be that even if you don't train the branch predictor, you could just work harder and make more iterations and still make this attack work out. And in that case, probably the victim process probably needs to follow these rules to avoid gadgets in its address space, for instance. I think it's still actually quite early to figure, the reason this lecture is kind of complicated is because I think people actually haven't figured out how to think clearly about these side channel attacks. It's all these caveats and this and that and a very complicated picture without a clear answer of oh, do this and you're good. So it's really a bunch of different things the CPU does that are speculative and here's a list of 9 that Linux does and there's a bunch of others that Linux doesn't even list here. I think, maybe in, I don't know, a couple of years, maybe we'll have a better idea of how to think coherently about this stuff. But right now it's kind of a, interesting, exciting time, if you will. Questions? Yeah. Why does the percent trick work? So what this does is that it actually emits code. This you mean? So this solves the problem. Why doesn't it solve this problem? This does solve the problem, but it requires you to find all the code that looks like that gadget in your program and add this percent to it. It has a cost because now the CPU has to do this needless divide instruction. Divides are slightly expensive, so it's not great. So your compiler probably shouldn't be adding these things willy-nilly every time it sees an array index. And the developer has to make sure they find all the gadgets. If they miss some, well, okay, you missed them. So the Linux kernel developers actually went through their whole source code, added this everywhere in a macro form that looks nicer. But it's a lot of effort to find them or find the ones that are needed, skip the ones that are not needed, etc. Other questions? All right, so this is, I guess, a fairly new kind of an attack. It really changed people's, I think, threat models quite a bit. I think people used to think, okay, fine, operating systems are understood. You can isolate many processes on the same machine. I think the way people think about sharing machines now is that it's really dangerous to share a CPU with someone you don't trust because there's a lot of state that could leak through the CPU. So that's pretty tricky now. That's one big deal of people thinking about threat models. But as I mentioned before, in practice, the effect it had is really more in terms of systems having to mitigate them and having to pay maybe some performance cost, as opposed to there being sort of dramatic compromises as a result of this. And partly because as soon as these attacks were disclosed, Linux sort of developed these mitigations pretty quickly. So there wasn't really a time when, for years or years, these systems were vulnerable, we didn't know what to do. Pretty much right away, we knew what to do. We did it. There was a performance cost, then it got better. So it's really more of a shift to what your threat model looks like, as opposed to some dramatic attacks that we saw happen as a result of these vulnerabilities. Question? Yes, okay, so the question is like, why does the paper make such a big deal about branch prediction? And the answer is, so you're right that the first attack I showed is not about branch prediction. It's easier to understand in some ways. The thing is, those meltdown style attacks are easier to fix because the permission checks are easier and cheaper to move up front in the speculation pipeline. The reason the paper makes such a big deal about branch prediction is because it is, at the end of the day, the hardest thing to solve for performance reasons. All right. So that's it for speculative execution. Happy to answer other questions if you want to come up afterwards, but that's it. See you guys next week. We'll talk about secure hardware. How much of a performance boost is branch prediction? It is absolutely massive. That's like, your system, it depends on the workload, of course, but like, your system could easily run, 10x slower without branch prediction.